Hello. So today is our first day of chapter 9. And before we actually get into chapter 9, we're going to review some things about radicals, which radical is just a mathematical way of saying a root. You should have learned really all of this in Algebra 1, but we're going to review it before we move on because it's pretty important. So this is saying at the top, it's just defining a radical. A radical is an expression that uses a root symbol. Like I said, the most common kind of root is a square root, but there are many other roots as well. So vocabulary-wise, it's important to know what perfect squares are. So perfect squares are numbers that have whole number square roots. So first I'm going to develop a list of perfect squares that we're going to be using throughout the chapter today. So not just today, but every day. So the first perfect square is 1 squared is 1. You guys already know all these, or at least you should. So fill in as far down as you can. 2 squared is 4. 3 squared is 9, etc. I know in Algebra 1, because we're actually doing this right now, that we do memorize all of these. And this helps us with perfect squares because therefore we know the square root of 121, for example, is 11. 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. So in order to simplify radicals, again, you definitely did this last year, you want to not just type the expression in your calculator. That is not the goal. So for example, to simplify square root 20, we're not just typing square root 20 and writing the decimal. We're trying to break down the number under the root so it's as small as possible. So we want to find the largest perfect square that the number under the radical is divisible by. Then we rewrite it as a product of those two factors. I'll show you what I mean by that in a minute. Take the square root of the perfect square and then take it out of the radical. And then just leave the leftover under the radical symbol. So square root 20, for example, is our first one. You're looking at your list of perfect squares. You're trying to find the biggest one that goes into 20. Turns out that 20 is divisible by 4. So we'll use 4. So we're going to change square root 20 to square root 4, square root 5. The square root of 4 is 2. So it's 2 root 5. Sometimes a common mistake that I'm sure you probably talked about last year, but just in case, would be the square root of 20 equals square root 10, square root 2. That is true, but root 10 and root 2 are not perfect squares, so it doesn't actually help you simplify it. So you don't want to use that one. So 300 has many factors. It has many numbers it's divisible by, but the one that we want to choose is 100 times 3, because 100 is on our list. Then the square root of 100 is 10, so it's 10 root 3. 147. I'm not super familiar with the factors of 147, but if you just start dividing by these numbers on this list of perfect squares, remember you want the one on the list to be as big as possible. So sometimes people suggest to start at the bottom of this list. Let's see, visually I'm seeing 49, and 147 is divisible by 49. So it'd be root 49, root 3. Always write the perfect square first. It just looks more normal in math. The next one is root 76. So we're trying to think of a perfect square that goes into 76. So looking at this list of perfect squares, let's see, 76 is divisible by 4. So let's use root 4, root 19. Because 4 times 19 is 76. The square root of 4 is 2. So it's 2 root 19. The next one is square root 190. Thinking of a perfect square that goes into that. I actually don't know that I see any. 190 is not divisible by 4, so it's not divisible by 16. I really don't see any. So if there is no perfect square that goes into it, you actually can't simplify it any further. So that's as simplified as it can get. Same thing with square root 13. So that's as much as you can do with. The U-trace, I'm just going to leave blank for now. So moving on to the next page. The next page is operations with radicals. So when you have coefficients outside the radicals, coefficients just means like numbers in front of the radical. What you do is you just want to simplify the radical first. So square root 36 we know is 6. So it's 4 times 6, which is 24. Similarly, square root 25 is 5. So it's 10 times 5. 10 times 5 is 50. Square root 200. 200 is not a perfect square. So we want to think of our list of perfect squares. Sometimes it's helpful to just kind of rewrite it, especially if you're not very good at writing it out. So 200 is divisible by 100. The square root of 100 is 10. So we have this. 2 times 10 is 20. So we have 20 root 2. And then 3 root 75. Square root 25 would be, square root 75 would be square root 25 square root 3. The square root of 25 is 5. So we have 3 times 5 root 3. You can multiply those numbers outside of the radical, so you have 15 root 3. So another thing, and then there's just more examples of this same concept kind of underneath it. We probably won't fill those all out, but I will upload them on Google Classroom later. So here we're multiplying and dividing radicals. Remember, radicals just mean roots. So we have square root 2, square root 32. So since they're both square roots, we can put them underneath the same square root symbol. So we have square root 64, because 2 times 32 is 64. The square root of 64 is 8. The next example is somewhat similar. They're both square roots, so they can go under the same one. 3 times 12 is 36. 36 is a perfect square, so you get 6. The next one, they are both square roots, but it's division. So you can put them underneath the same root. So it's square root 1400 divided by 2, which is 700. Then we want to break up 700, much like we did on the previous page. So we're going to use 107. So the square root of 100 is 10. So we have 10 root 7. Next one, similar. We have square root 600 divided by square root 2, so I'm going to change it to square root 300. The square root of 300, I can make it 100 times 3. The square root of 100 is 10. So it's 10 root 3. Again, those more examples I'm going to leave blank for now, but I will upload on Google Classroom later if you're curious about any of them. Another important topic with roots is rationalizing the denominator. So rationalizing the denominator means that you can't leave any roots in the denominator. So the bottom of the fraction can't have a root in it. So to get rid of it, you multiply the top and the bottom by the radical, then simplify if needed. So here I'm going to multiply by root 5 over root 5. Root 5 over root 5, anything over itself equals 1. So you're not actually changing what it equals, you're just changing how it looks. So just multiply straight across, just like we always do with fractions. So the top of this is 1 times root 5, or just root 5. The bottom is root 5 times root 5. They're both roots, so you can make it the square root of 25. The square root of 25 is 5. So there's just a regular 5 on the bottom. Similarly with the next one, you always just multiply by whatever root's on the bottom. So the top of this, multiply straight across, we have 4 root 6. The bottom, we have root 6 times root 6, which is going to be root 36, which is 6. So then the last thing we can do is we can simplify 4 over 6 is 2/3. So you can simplify that. So you have this. Then we have some u-tries that are similar to the ones that we just did. Then looks like there's some more kind of complicated examples. So I'll go through those. Here we can simplify 6 over 2. 6 over 2 is 3. So it's 3 over 1. So it's just 3 over root 7. You can't leave that root 7 on the bottom. So you have to multiply like that. So you have 3 root 7 over 7. The next one, we can't leave that root 2 on the bottom. So we want to go like this. On the top, we have 1 times root 2, which is root 2. On the bottom, these two, root 2 times root 2 is the square root of 4, but that's 2. So that whole thing is really just 2. So we have root 2 over 6. And then on the next one, We can simplify these numbers outside of the root. So that simplifies to 1/3. So I'll do that right away. Then on the bottom, the numbers outside of the root are 5 times 3, which is 15. We can't leave that root on the bottom. So multiply by root 3 over root 3. So you end up having root 3 over root 3 times root 3 is 3. 15 times 3 is 45. And just one more of those. Here I have 12 times 4 on the top, which is 48. Root 2 divided by 8. You can divide these numbers that are not under the radical. So 48 divided by 8 is 6. So we have 6 root 2. Okay, the next, there's some U tries on the bottom. I'll load those later. What we have left is just like solving equations with radicals. So that is what we're doing now. So to solve equations with radicals, you solve for x like normal, and then you have to rationalize the denominator, meaning get rid of that root that's in the bottom. So we want to divide by root 3 over root 3 here. So we get x equals 12 over root 3. We can't leave that root 3 on the bottom, so we have to rationalize it. So multiply by root 3 over root 3. So on the top, multiply straight across, we get 12 root 3. On the bottom, we have root 3 times root 3, which is root 9, but the square root of 9 is 3. So we have this. Then you can always simplify the numbers outside of the radical, or outside of the root. 12 divided by 3 is 4. So we have 4 root 3. That's how you do all of those. So then there's a few U tries that I can go through here. Maybe just the first one or whatever one looks the most complicated. I think I'm going to do the last one because it probably looks the hardest. So to get x by itself, I want to get rid of that root 2. So I'm dividing by root 2. So I get 14 over root 2 equals x. I can't leave that root 2 on the bottom. So to get rid of it, I want to do what's called rationalizing it. So you're going to multiply by root 2 over root 2. On the top, we have 14 root 2. On the bottom, we have root 2 times root 2, which is square root 4, but the square root of 4 is 2. So whenever you have a root times itself, the root just cancels itself out. Now just divide the numbers that are not under the radical. So I have a 14 divided by 2, which is 7, and then root 2. Okay, so that is it. Like I said, I'm happy to upload this key so that you can see all of them. I did feel like I wanted to go back and do a couple of these if I had time. So I do want to go back to these bottom examples here. This one's kind of like one of the ones we already did, but they're both square roots, so you can put them under the same radical symbol. So it's 400 divided by 100, but that's 4. So the square root of 4 is 2. So your answer there is 2. The next one, you want to start by simplifying root 24. So root 24 would be root 4 root 6. So then we have 3 on the top. The bottom I have a 4 times a 2, because the square root of 4 is 2. So outside of the root I had this. Then I can't leave that root on the bottom, so I have to rationalize it. So on the top I have 3 root 6. On the bottom, these two make a regular 6. So on the bottom, I have 8 times 6, which is 48. It's kind of a long one. Then you can simplify. The 3 over 48 is 1 over 16. So it's square root 6 over 16. The next one actually is kind of short. You would just simplify the square root of 45. It's root 9 root 5 over 10. And then the square root of 9 is 3. So it's just 3 root 5 over 10 on that one. And then the last one is root 9 over root 4, which you might be like tempted to put them under the same root and make it the square root of 9 over 4. That actually doesn't really do much because 9 over 4 is not divisible. So what you want to do here is just square root them individually, and you get 3/2. So kind of the key to radicals is just that list of perfect squares and breaking them down with that. So you do have some homework tonight. It's a worksheet, and it does need to be done by tomorrow. tomorrow we're moving on in this unit and moving on to some more geometry things. So I hope to see you tomorrow. My daughter's sick, that's why I'm not there today, but hopefully I can be there tomorrow. Make sure you do your homework.